Hi, this is Pat Kelly. Okay, in this problem, they give us this vector-valued function, okay, given to us here, and they also specify a point that's going to be on the surface of that function. And our job is to find the equation of the the plane that would be tangent to this function at that point. Okay, so three-dimensional space, this is going to produce some kind of surface for us. That point would be on the surface. We're looking for the plane that would come and touch the surface at that point. Okay, roll up your sleeves. We've got a bit of work to do. All right, now the first thing I would want to do is the point that they give us is, you recognize it, x comma y comma z. I mean, it's an ordered triple. So it's in terms of x, y, and z. That's what would worry me. Not worry so much, but before I move on, I need to get that same point in terms of u and v rather than x and y and z. Okay? So in order to do that, what we're going to do is look at your x, y coordinates in the function, and you know that you can see those from the components of I and j and k, respectively. And then realize that each of those would end up equaling those values for x, y, z. And so you try to set the expression equal to one of those values and then solve. Right? Maybe easier said than done sometimes, because it depends how involved these expressions are. So let me talk you through what I would do in my approach, is that this expression involves both u and v. This one involves both u and v. So I would definitely pick on this one first, because it only involves one of the parameters. So what I know is that for sine of v at that point of tangency that we want has to equal the z coordinate of 2. And you see what this is going to allow us to do is solve for v. Sine of v equals 1/2. Let me slide over. I'm going to need a bit of space here. So where does the sine of v equal 1/2? V is going to have to equal pi over 6. All right. Now that we have a specific value for v, I can actually grab either one of those first two components, put in that value of v, and solve for what u will equal based on either one of those other coordinates. I would pick the first one. You got to love a 0, right? So that comes from this first component. So I now know that 3 cosine of pi over 6 times cosine of the unknown u, well, that's got to equal to 0. All right, well, I know cosine of pi over 6 doesn't equal 0, so this cosine of u must be what's getting us to 0. So where does cosine equal 0? And that's going to be pi over 2. All right, a little bit of work, got to do it. That gets you this point. Maybe I'll even keep color coordinated for you. But it gets you this point in terms of u comma v. So my u is pi over 2. My v was pi over 6. And I will definitely be using those coordinates for my parameters. All right, let's move on. The next work you need to do is we're going to do some calculations of some partial derivatives on that r vector, r function. First, I'll do r as a partial derivative with respect to u of this uv. So go ahead and differentiate with respect to u. This looks like it's going to be a minus 3 cosine of v sine of u times I. Differentiating with respect to u, that'll be a minus 2 cosine of v. Differentiating with respect to u, this should have been a positive then, right? Sine would just become cosine. Yep, that looks good. J vector. And then differentiating with respect to u, that one disappears, so that's nice, 0k. Okay. Now I also need to do the same differentiation, but this time a partial with respect to v. Before I do that, though, I'd like this r differential, partial differential with respect to u, with the specific arguments of pi over 2 and pi over 6, my u and my v. Okay, we're going to want those specifics plugged in and find out what this R derivative is at that point. That's what we're doing. All right, so I'm going to plug in minus 3 cosine of v is cosine of pi over 6. That's square root of 3 over 2 times my sine of u. Sine of 1/2 is 1, and that's times the I vector, plus 2 times cosine of v again. That's going to be your square root of 3 over 2 again. This time, though, my cosine of u here, cosine of pi over 2, that blanks out to 0, so that's nice. Okay. And then the j vector, and then plus, and we really like that one, that's still just 0k. And let's just rewrite that to clean it up and not see all these zeros. So I'm just looking at a minus 3 square root of 3 over 2 times the I. All right. Okay, back over here. Let's do that other partial that we mentioned. We need that R function, partial with respect to v, uv equals. Okay. Then I'm looking up here, but differentiating with respect to v. So then I'm looking up here, but differentiating with respect to v. So the derivative of cosine is going to be a minus sine v. Cosine of u stays the same. I vector. Differentiating with respect to v, so here's another cosine. That'll be minus 2 sine v times the sine of u times the j vector. And then plus, this one does have representation this time. Doesn't blank out to 0. We get 4 cosine of v times that k vector. Okay. All right. And as I did before, I'll do the partial this time with respect to v of the specific u, pi over 2, and the specific v, pi over 6, equals, just looking right above here, minus 3 sine of v, so sine of pi over 6, that's half. And then cosine of u, so cosine of pi over 2, that's 0. I vector, minus 2 sine of v, so there's your sine of pi over 6 again, that's still a half. And then sine of u, sine of pi over 2, that's going to be 1. And that's my j vector, plus 4 times the cosine of v, cosine of pi over 6. That's the square root of 3 over 2. And that's my k vector. Let's also try to do a rewrite and clean that up a little bit. I mean, at least we get one blank out here of the 0. And then 2 1/2, that's just going to be a minus j, plus, and then 4 and 2 looks like 2 square root of 3 times your k. All right, I'm still taking a breath though because we have more to do. What you do with these two partials, if I come down here, is we cross them. So I'm going to look at r with respect, partial with respect to u of uv, you know the arguments. What we really want to work on is the mechanics, and what we're doing mechanically is crossing those two vectors that we just found. This equals. And what I do typically for this type of cross product is set up this I, j, k, and then you fill in your other rows using the components of each of those vectors as rows. So my r sub u was here. I only have the minus 3 radical 3 over 2 as a component. I only have that. So the others are zeros. The same thing for the third row. So I'm going to put the components in of rv. So now I'm looking there. First one's 0. Second one is a minus 1. And then we have that 2 square root of 3. And I need all of that. Okay, so this equals, and I would grab my I component and do a crisscross here, and that's actually 0 minus 0, so that's 0, that's good. Minus, when I go to get my j vector, now my crisscross goes here, 0 times 0, minus this times this. And since there's already a minus there, that's actually going to become plus. When I multiply these two guys, you can see the 2's are crossing out. Square root of 3 times square root of 3 is 3, times the 3 that's there is 9. And then plus my k component. And now I'm doing a crisscross this way. Minus times a minus, so it's going to be positive, and it's, you know, this times 1, so it's going to be that 3 square root of 3 over 2. Minus the other, the crisscross, but I was looking ahead, that's 0, right? So this is our cross product right there. What's the significance of that? That's one of those normal vectors, okay, which you can use to write the equation of the plane, which is what we want. So we're like one step away from our answer here. Let's take that step. Now, the way you utilize this normal vector is, I'll switch to colors, a little a cramp for space, but right here in orange, let me write my equation of that tangent plane. Right? So the way we use this normal vector is by looking at the coefficient, if you want to view it that way, or component, that's 0 for the I vector, the I direction. And you multiply that by x minus, and I got to go up here all the way to the original x, y, z, and the x right there is 0. I really didn't care too much because it's going to multiply by 0 in a second. But then plus, you grab the next component, or coefficient, 9, y minus, I go up there again, and the y coordinate of that point of tangency was square root of 3, plus, and then I grab the third component, the k component, which is 3 radical 3 over 2. And you do the same thing, continuing with the z variables, z minus 2 in this case, and that equals 0. Okay, that's a good equation for the tangent plane. I'll clean it up just a little bit. It looks so sloppy right now. Zeros blank out. Let's get our variables on one side, so 9y, plus, as ugly of a coefficient as you might think that looks, you write that times z. And let's see if I can throw the constants on the other side. So I would have 9 square root of 3 would have been negative, throwing it to the other side. And then minus 2, that'll also become positive. The 2's will cross out. Looks like 3 square roots of 3. And I should definitely combine those and make it a 12 square root of 3. And a huge sigh of relief. That's the end of the problem. Okay, that's your equation for the tangent plane in this problem. Okay, hope that helps. You can see you definitely need to practice some on your own.